Good morning. Today, our group, we would like to present for our subject MAT222 Mathematical Logic and Proving Techniques. For our group members, we have 5 members. Me myself, Kerry Kelvin, and we have Erfan, Muhammad Azri, Ahmad Fan Adli, and Kaldios Zapri. For the table of content, we have 2 chapters we are going to present, which is for the first one is chapter 2, logic, and chapter 3 is proving technique. In chapter 2, we have 3 subtopics we are going to present. For the first one is logical equivalence, second, laws of logic, and third one is quantifier and nested quantifier. For logical equivalence, compound propositions that have the same truth values in all possible cases are said to be logical equivalence. In definitions, the propositions P and Q are called logically equivalent if P equivalence Q is a tautology. To determine whether two propositions logically equivalent, one way is by using truth table. So the truth table is a way that on how we are going to find either both of the proposition are logically equivalent. The propositions P and Q are equivalent if the volumes giving their truth values are the same. For example 1, show that P equivalent to Q when the other propositions is negation P equivalent to negation Q. For this question, we are going to solve using truth table for sure. Then we are going to find the truth values of P, which is true, and false, and Q, true, and false. Then look at the question. We are going to find P and also negation Q of their truth values. Then we need also to find the values of negation P equivalence to negation Q. And we also need to find P equivalence to Q. By looking the values of negation P equivalence to negation Q and P equivalence to Q, we see that both of the truth values are the same. Therefore, both of them are equivalent. For example 2, we also have question P equivalent to Q when P and Q or with negation P and negation Q. Find the truth values of P and Q and also P and Q, negation P, negation Q, also with negation P and negation Q. Then we'll need to solve the question by answer the truth values of P and Q or with negation P and Q, and find also the truth values of P equivalence with Q. We can see that both of the truth values are the same. So therefore, P equivalence to Q when the other proposition is P and Q or with negation P and negation Q. For example 3, show that negation P equivalence with Q when the other propositions is P equivalence to negation Q by using truth table. Find the truth values of P, then find the truth value of Q, also with P equivalence with Q and negation P equivalence with Q, and also we need to find the values of negation Q and P equivalence to negation Q. By looking the both of the truth values of negation P equivalence with Q and also P equivalence with negation Q, we see that both of the truth values are the same. So therefore, negation P equivalence with Q is equivalent to P equivalence to negation Q.
Next, we move to the next subtopic, the law of logic. The law of logic are fundamental principles that govern valid reasoning. They provide a systematic framework for analyzing statements, constructing logical argument, and determining truth or falsehood in a consistent and rational manner. In this chapter, we need to know several of the laws. Double negation law states that Negating a statement twice brings it back to its original meaning. In other words, not P is the same as P, so the statement is true again. De Morgan's law explains how the negation affects N and OR. When the statement with OR is negate, it becomes N with each part negate. And when a statement with N is negate, it becomes OR with each part negate. Commutative law show that the order of the statement does not affect the result. For example, P or Q is the same as Q or P, and P and Q is the same as Q and P. Associative law states that the grouping of statements does not change the meaning. This means P or Q or R is the same as P or Q or R, and this same applies to N. Distributive law explains how N or can be distributed over each other. N can be distributed over R, and R can be distributed over N to rewrite logical statement. Idempotent law means repeating the same statement does not change anything. Therefore, P or P and P are the both equal to P. Inverse law states that combining a statement with its negation gives a fixed result. P or not P is always true, while P and not P is always false. Identity law shows that combining a statement with a neutral value does not change it. P or false and P and true both remain equal to P. Domination law explains that combining a statement with true or false can dominate the result. P or true is always true, while P and false is always false. Definition of implication states that if P, then Q is equivalent to not P or Q. The implication is false only when P is true and Q is false. Definition of biconditional means P if and only if Q. It is true when both P and Q have the same truth value. Absorption law states that a statement can absorb extra part without changing its meaning. For example, P and Q and P or Q are both equal to P. Now we apply the law into the example. In example 1, we simplify the statement P or negation P and Q. First, we apply the De Morgan's law to remove the negation inside the bracket, which change N to OR and negate each part. Next, we use the double negation law to cancel the double negation on P. Then, by the associative law, we regroup the statement. Finally, using the idempotent law, we remove the repeated P. The simplified form is T or negation Q. In example 2, the expression is negation A or negation B or A and B and negation C. We first rearrange the term using the associative law. Then we apply the De Morgan's law to rewrite the part of the expression. After that, we use the distributive law to factor common terms. When a statement is combined with its negation, we apply the inverse law, which gives the true value. Using the identity law, we remove the truth value and finally apply the De Morgan's law again. The final simplified expression is negation A or negation B or negation C. In example 3, the expression is A and B or A and B and negation C and D or negation A and B. First, we regroup the term using the associative law. Then the absorption law allows us to remove the unnecessary part. Next, we apply the distributive law to factor out B. Since A or negation A is always true, we use the inverse law. Finally, the identity law removes the true value, leaving the simplified result is B.
My name is Muhammad Azri bin Muhammad Nazrin, and today I'm gonna talking about Topic 2 about quantifier. Universal quantifier. The universal quantifier of Px is the proposition Px is true for all value of x in the universe of discourse. For example, question is Rx x square minus 1 greater than 0, universal all real number. For all x, Rx equal to false. And the counter example is x equal to 1, then we put x equal to 1 in the equation x square minus 1 greater than 0, and we got 1 square minus 1 greater than 0. The answer is false because the final answer we got is 0. 0 does not greater than 0. Existential quantifier. The existential quantifier of Ps is the proposition there exists an element x in the universe of distance such that Ps is true. And the example question is sum of x equal to x plus 1, universe all real number R. X equal to x plus 1, and we put 1 from the right into the left, and we 1 equal to x minus x. Final answer is we got 0 equal to 1. The answer is false because no x satisfies x equal to x plus 1. Nested quantifier. Nested quantifier are quantifier that occur within the scope of the other quantifier. There exists a real number y for every real number x such that x plus y equal to 0, universal or real number. Sum of y, all of x plus y equal to 0. The answer is false because not all x we can use in the equation to get the answer is 0. For example, if we put x1 plus y we put 0, we did not get the answer is 0, and 1 plus 0 not equal to 0. That's the example for why the equation is false. Logical expression involving quantifier. Translating English or other language statement into logical expression is crucial in mathematics, logic, programming, software engineering, etc. There can be many ways to translate a particular sentence. Example 1. Determine the true value of each statement below. The universal set is the set of a real number. Justify your answer by giving example or counter example. For question A, all x, all y, x square less than y plus 1. The answer is false. For question B, sum x, sum y, x square less than y plus 1. The answer is true. For C, all x, all y, x square plus y square equal to 9. The answer is false. And for question D, sum x, sum y, x square plus y square equal to 9. The answer is true. And for question E, sum x, all y, x square plus y square greater than equal to 0. The answer is true. For example 2, translate the following into logical expression. Given the open statement Px, x is a lion, Qx, x is a fish, Rx, x drink coffee. Universe, all creatures. For question A, all lion are fish, and we can use all x Ps implies to Qx. For question B, some lion do not drink coffee. We can use some x Ps and negation Rx. And for question C, all creatures that are not fish drink coffee, and we can use all x bracket negation Qx implies Rx bracket. And for question D, no fish creatures drink coffee, and we can use some x bracket Qx and Rx bracket. For example 3, determine the true value of each of the statement with the indicate universal set. Then negate the statement. For question A, all x, sum y, x plus y equal to 0, universal set equal to z, the set of integers. The answer is true. For question B, sum x sum y, x plus 5 equal to 2 plus y, universal set equal to 0, 1, 2. The answer is false. For question C, sum x all y less than x, universal set equal to n, the set of natural number. The answer is false. And for question D, all x sum y, x less than y square, universal set equal to set of positive real number. The answer is true.
For the chapter 3, we have 1.0, which is introduction, and the forward and backward method. So for 2.2, we have the contradiction method and the contrapositive method. Okay, so for the forward process, we have the conclusion, which is it begins with given facts, premises or assumptions, and proceeds step by step toward a conclusion using logical rules. So for the backward process, it means that it starts from a conclusion and works in reverse to determine the conditions or premises required to make the conclusion to be true. So for example 1, which is for the forward process. For the example 1, using a simple implication. So for the premises, we have number 1, it is if it rains, then the ground is wet, so that it is P implies with Q. For number 2, we can put it as it rains, and 3 can label it as P. So next, from P implies with Q, and from P we conclude that Q. So for the conclusion is the ground is wet. For example 2, we using a chain reasoning. For the premises, if a number is even, then it is divisible by 2. So it will be P implies with Q. So for the second one, if a number is divisible by 2, then it is not odd. So we can conclude it as Q implies with R. Then the number is even. We can label it as P. For the forward reasoning, from 1 and 3, we can get a Q. Meanwhile, from the 2 and Q, we can get R. So for the conclusion, the number is not odd. Next, the last example for forward process, we use a conjunction. So for the premises, if a student studies hard, then the student pass the exam. So we can use P implies with Q. For the next, which is the students studies hard and attend class, can use P and R. Forward reasoning, from P and R, we can extract P. And then from P implies with Q and P, we can get Q. So for the conclusions, we can conclude that the student passed the exam. Next, for the example of backward process. For example 1, we use a simple implications, which is from the conclusions, which is the goal, can conclude that the ground is wet, so you can label it as Q. For the rule, if it rains, then the ground is wet, can label it as P implies with Q. For the backward reasoning, to prove Q, we need to prove P. And for the premises, if it rains, then it should be P. So the conclusion is, therefore, the ground is wet. So for the example 2, we use a chain reasoning. So for the conclusions, you can conclude that the number is not odd, so it is R. And for the rules, is number 1, if a number is divisible by 2, then it is not odd. Can conclude as Q implies with R. The next one is, if a number is even, then it is divisible by 2, so it will be P implies with Q. For the backward reasoning, to prove R, we need to prove Q. In order to prove Q, we need to prove P. So for the premises, the number is even, so it is P. And the conclusion is, the number is not odd. And the last example for backward method, we use a conjunction. So for the goal, the student passed the exam, so it is Q. And for the rule, if a student studies hard, then the student passed the exam. So it is P implies with Q. For the backward reasoning, to prove Q, we must prove P at first. And for premise, the student studies hard. And for the conclusions, the student passed the exam. So that's all from me. Next we
The choose method. Choose method used in the backward process that contain universal quantifier. Example, for all, for each, for every. Such statement occur frequently in set theory. Set theory. A set is collection of objects. Each object in a set is called a member or element of the set. Member of we label as E, not a member of we label as not E. A set is denoted by enclosing the list of its members, separate by commas in set braces. Example, A equal to bracket 2, 4, 6, 8. Set which very large number of members or sets with infinite members can be denoted by using set builder notation. A set is said to be empty if it has no members. Notation, empty bracket or null set. First example, we have two sets of P and Q and their elements. First, hypothesis and conclusion as A and B. Then, for B1, define B as for all elements add subset to P, add subset to Q. And for A1, we choose an element other than X in P, so we use P subset to P. Then, B2 will be P subset to Q. For A2, we change our X to P. Then, for A3, we factorize it. For A4, we have two possibilities and one of that is wrong. For A5, we show the wrong one. So for A6, we choose the right equation, that is P plus 1 greater or equal to 0 and P minus 4 less or equal to 0. For A7, P subset to Q, then the answer will be negative 1 less or equal to P less or equal to 4. Second example, we have two sets of S and T and their elements. We must show that T subset to S. First, we write hypothesis and conclusion as A and B, and then for B1, define the B as for all elements T in T. T is in S. For A1, we choose an element, say T1 in T. Then B2, we say T1 is in S. Then B3, we substitute T1 in equation. For A2, we substitute T1 in inequalities. For A3, we separate them into two inequalities. For A4, we make the inequalities greater or equal and less or equal to 0. Then, for A5, we combine them. For A6, we simplify it. Lastly, we got A6 that logically equivalent to B3. For third example, we have two sets of P and Q and their elements. Then, they want to show that Q is subset to B. First, we write hypothesis and conclusion as A and B. And then, for B1, define the B which is for all elements in Q is in P. B2, we show that X prime is in B. We substitute X prime in the inequalities of elements in P, which we will get B3. After that, we choose an element that say X prime in Q as A1. Then we substitute X prime in the inequalities of element in Q. Then we separate them into two inequalities and combine them to be one inequalities which less or equal to 0. Then we simplify it. Finally, we got A5 that equivalent to B3, which make this statement proven to be true. Conclusion. In chapter 2, we understood that to find the true values, we can use truth table method while law of logic is to simplify statement and determine whether arguments are true or false. For quantifier is telling us how many elements in a set make a statement true. In chapter 3, we can conclude that the forward method and backward method are reasoning techniques used to prove statement or solve problem, especially in predicate logic, proof, and computer science. For choose method is a way to prove statement involving for all or sets by selecting an arbitrary element. Thank you.